So who in the audience would describe themselves as developers or computer engineers with a new skill set in machine learning? Quite a few. So that's a good thing. And I would like to share with you a couple of tools that you can use day to day to work faster and more efficiently. TPUs is of course one of them, but there will be a couple of others. So this is a TPU V2. This is a TPU V3. Those are fairly large boards. It's like this, roughly. And each one of those boards has 4 chips. Each chip is a dual-core chip. And those accelerators are designed specifically to accelerate machine learning workloads. You can get them as boards like this. You can also get them as a full rack. It's called a pod. And the trick is that in a rack, all the TPUs are interconnected on a high-performance interconnect, which makes them look like a single accelerator to your workload. So you don't have to handle complicated distribution code. The only thing you do is you increase your batch size to work on those bigger machines. And just a couple of words of what makes them special inside of a TPU. So a board, 4 chips, 8 cores. In each one of those cores, you have 2 things. One is a fairly traditional vector processing unit. So that's a vector processor. And the second one, that is what makes this special for machine learning, is a matrix multiply unit. So there is a specific unit, hardware unit, that is dedicated to performing 128 by 128 matrix multiplications in reduced precision in a format called bfloat16. And machine learning workloads are full of matrix multiplications. So by having this dedicated hardware in there, this is what accelerates machine learning workloads specifically. Now, about this precision, so using reduced precision is a fairly common trick in machine learning. Usually you do so in float16, the standard float16 precision. But as you see here, float16 has only 5 exponent bits, so fewer than float32, which means that when you reduce the precision, sometimes you get underflows or overflows, and you have to do additional work on your model to overcome that. It's not necessarily complicated, but it's work. And so what we did in TPUs is that we used a slightly different 16-bit format called bfloat16, and you see it has exactly the same number of exponent bits than float32, just the end is cut off, so reduced precision, but exactly the same range. So usually bfloat16 is a drop-in replacement for float32 in neural network workloads. And also we do the multiplications 16-bit multiplied by 16-bit, which gives you a 32-bit result, and we keep this 32-bit result. And finally, the way it's architected is that we have, so try to remember from your calculus courses how to perform a matrix multiplication. Each result is a dot product of 1 line of one matrix and 1 column of the second matrix. And a dot product is a series of multiply and accumulate operations. Multiply plus, multiply plus, multiply plus. So that's why the unit component of this array is a multiply accumulator. And by having 128 by 128 multiply accumulators connected like this, I'm not expecting you to understand this animation immediately. You will have to spend a little bit more time on it, I guess. But the idea is that you load one matrix into the array. The other matrix, the values, they flow through the arrays. All the intermediate sums, they flow through the array in this direction. And what comes out from this end are your final dot products of the resulting matrix. So it's a one-pass operation. No memory access while you're doing this, no writing to registers an intermediate sum and reading it back, which is why it's fast. And the second advantage is that the unit of processing, the 16-bit by 16-bit to 32-bit multiply accumulate, it's a tiny piece of hardware. It's not a full processor that can do anything. It's just a multiply accumulator. And that's why we can cram a huge number of them in each TPU. Each TPU core, 128 by 128, 16,000 of those multiply accumulate compute units. And of course, a TPU is dual core, so 32,000 in total. And this is the architecture, so specifically for matrix multiplications, that gives TPUs an edge in terms of density. Density means power, and power means cost. A rough idea of the cost. Some people might have seen my talk from last year about building this model. And I'm using this model as a benchmark these days. So this model trains in 4.5 hours on a GPU. And if I provision 5 GPUs in a cluster, I can train it in 1 hour. And I chose this example because I can train it in 1 hour also on a TPU V2. So the rough idea is this 4-chip board is roughly equivalent to 5 of the biggest GPUs that we have in terms of speed, and in terms of cost is roughly 3 times cheaper. So I could go on forever and bore you to death with all the technical details. And if you ask me questions, I will. But this is the dev zone, so you want to see code. So let's get code on the screen. I love notebooks. I will be using notebooks. And by the way, have you seen that in ML Engine, there is this new notebook instances button where you can provision a new instance already set up for TensorFlow or PyTorch with a GPU. And also, I set one up with a TPU. So what you get is a link that opens Jupyter Lab. Actually, I had it open already. That's why it's doing this. So let's go in my instance here. And before we start using TPUs, I have to tell you a couple of things about data, how to load data. Because TPUs are very, very fast accelerators. And the first problem you're going to encounter with TPUs is not being able to feed them data quick enough. So let's talk about data. In this, I will be working with a data set on this model. It's a detection data set of wildlife photography. So you see my classes coming up in this notebook, goldfish, shark, and so on. But those are just the metadata. What I want to show you is how I load my images. So here it is. I will be using the tf.data.dataset API. And that's an API that is designed to prepare data sets for training. So it has all the natural function calls that you need for repeating across multiple epochs, batching, shuffling, and so on. How does it work? So the first line here is list files. I give it a folder, and I obtain a data set of file names. Then the API allows me to map any function on that data set. Here I'm mapping a decoding function, this function, which has image.decode JPEG and read file before it. So now I have from my data set of file names, I have a data set of images. Then I need to resize and pad them. So I map this function, which does the resizing. And then I repeat, I can shuffle it, I batch it into by 16. And the API also, this is interesting, the prefetch call, you can use this to tell TensorFlow to prefetch the next batch while it is training on the current batch. So let's try to run this. How do I iterate on a data set in TensorFlow? Well, now you can do 4 images in data set, just a normal loop. This only works in eager mode. I'm in TensorFlow eager mode. So you see, I'm just displaying here the shape of my tensor, batches of 16 images of 384 by 384, and it's painfully slow. It's horrible. I wait seconds for 16 images to come up. Why is that? Well, the reason is that I'm reading for GCS, Google Cloud Storage, which is a good thing. From GCS, you can get a crazy throughput. But GCS is a storage that is attached through IP, the internet, and it has a per file penalty. This data set has 300,000 images. You will not load it image by image. That does not work. So what is the right way of doing it? The correct way is to batch your images into some file format that can contain multiple pieces of data at once, some kind of record file format. In TensorFlow, you usually use the TF record file format, but really, it has nothing special about it. It's just a file format to cram multiple pieces of information in one file with tags. So how does this work now? Again, tf.dataset list files. I have a dataset of file names. This time, I have done the pre-processing of my files. So I'm reading from a different folder that has these TF record files. Then I instantiate from that TF record dataset. So now I have a dataset of records. You have noticed that I'm actually doing it through this interleave function, because this is how I can read from 16 different files at the same time. And that's how you get the throughput. You batch your images into big files, 100 megabyte TF record files, and then read from 16 of them at the same time. And then map, repeat, and everything else. Let me show you that. And of course, the decoding function here is this function where I simply unpack what I put in my data set. So what I put in my TF records is the image, some metadata, and since this was a detection data set, I have the bounding boxes and the classes of this data. So yeah, it has displayed it. It is a data set, detection data set. You see ladybugs, dolphins, and so on. And this time, well, look, this time my images are coming out 16 by 16 at a steady clip. So this is what you should do when reading from, when packaging data for consumption by training, and especially for TPUs. So now let's get training. We have our data set, let's get training. I'm switching here to a different notebook technology, which you might know. This is Collaboratory. That's a free service on Google where you get notebooks with a free backend. And actually, if I click runtime here, change runtime type, I can get a TPU accelerator for free. I love it. So this is a slightly different data set, but not very different. Let me do this. TPU detection, it says read running on TPU. Configuration, let me show what I'm here as well. I'm loading from a TF record data set. But let me show you what this data set is. It's a data set of images. So we will be classifying flowers here. And you recognize the familiar dataset API. I hope by now it's familiar with dataset.map, .repeat, .batch, .prefetch, and so on. So this is how I create my dataset. But now, and I'm working in Keras, so I hope most of you recognize this kind of Keras code, where you have a sequential model and a bunch of layers. The 3 lines of code I would like to attract your attention to are these 3. This is how you train a Keras model on TPU. 1 line to find a TPU, a 2nd line to define a TPU distribution strategy using that TPU, and a 3rd line to transform your model into a TPU model. From there on, you train it as you normally would in Keras. So let me launch the training here. You see I'm doing TPU model.fit, passing the data set. And what is going on is interesting. You see compiling. Actually, what is going on? My code is running on a VM, a normal VM. The TPU is attached through the network to it. TensorFlow defines my model as a computation graph. And it's that computation graph that is shipped off to the remote TPU for training. And from that computation graph, we use XLA, the Accelerated Linear Algebra Compiler, to compile that graph into TPU microcode. So the TPU never sees your Python code. You have to bear that in mind. It only sees your graph. But if you use the TF data dataset API, your data pipeline is also packaged as part of this graph. So the TPU will be pulling data directly from GCS, which is very efficient. And as you can see here, this is what I love about TPUs. On small to medium models, I can get training times of 4 seconds per epoch, and I can iterate in minutes interactively in a notebook on various models. This is a smaller model. This one has 3,000 images. But you see, it's already trained. 15 epochs. We will see if it trained well. Yeah, here is the accuracy. Fine, it got to 75%. And let us run a couple of predictions from it. See if it is classifying my flowers correctly. Running, displaying, here we go. So it doesn't get all of them right, but the dandelion is fine, the roses, the sunflowers, dandelion, and it mistook, well, this is a hard one. Right, it got a couple of mistakes, no model is perfect, but this is what I love about TPUs. It's really fast, and you can use them interactively. But now, I want to show you a bigger model, a bigger one, and for this, of course, a bigger model that we'll be training in half an hour, that is not something that you would be comfortable doing in your notebook, doing interactively on a machine. You don't want to be paying for an expensive machine to type code. That is only when you do interactive work. I want something that allows me to take a notebook and launch it as a job on hardware that will be provisioned just for that job and decommissioned when the job is finished. That is the Fairing API. So that's a new thing. Reminder, the 3 lines to get a Keras model on a TPU, the couple of lines to load a TF record data set, using interleave to read from 16 different files at once. But the last thing that I want to show you is a new API called Fairing. So let me show you the code. I'm back into my previous notebook with the detection model. And now, the Fairing API is just this. It has 3 lines. First, set builder to say something about my environment. I have actually built my dependencies as a Docker container. That's a couple of lines. I just have a couple of pip dependencies. The second one, which says, where are you deploying? I'm deploying to GCP, which is ML Engine. And this is the hardware configuration I want. I actually want a Cloud TPU v3 to be provisioned for this job and destroyed after the job. And finally, what am I deploying? I'm deploying a full notebook. This is a notebook-friendly API. I have the name of my notebook, and I have a couple of sidecar files which I listed behind it. Now, when I launch this, it will build all of those things into another Docker container. I don't have to know about Docker. It does it. And launch a job on ML Engine, which I think we will see here. Let us go to jobs on ML Engine. And right, I have 2 jobs running. This is a new one, has been running for 18 seconds. And I actually wanted to train this big model here with you on stage. In 20 minutes, it was a bit tough. You will have to come to my repeat session tomorrow to see this model actually built on stage. So I started it, you see, 37 minutes ago. That's the second job, just before I stepped on stage. And let me see if it has finished. Well, it looks like, yeah, it looks like we have a model. It's here. Where did I just lost it. It's this one. Let me open it, open this file. Downloads. And it's still downloading. OK, come on, download. The internet is slow here. So it will be downloading and then re-uploading. The uploading is the bottleneck here and not the training. But the result is actually a notebook. That is what I was saying about a notebook-friendly API. I like working on notebooks because I can do data preparation and visually eyeball my data set. I can have my training cell. Then I can play with the trained model and visually eyeball that it's doing the right thing. All that in a notebook. That is what I use when I do interactive work in a notebook. But then when I launch all that as a job, I don't want to lose all of that. So here with this API, still downloading, and then it will be uploading. Sorry, I will cheat and actually show you results from a previous run because we are running out of time. But here with this API, I can have all that as a job, and the result of the job, of course, is the saved model in the bucket where I told it to save my model and so on. But it's also a fully rendered notebook where I have all my cells rendered, and I can eyeball anything, all the graphs, all the visualizations that I have put in there.